Alrighty, good morning, guys. Can you hear me?
Yeah, we can hear you.
Alrighty. Are there any questions before we get started? Okay, if that's not the case, then there are two things on the agenda today, and so before the break, we're gonna start on a topic called change of measure, and traditionally this has been a difficult topic. So we're going to try to go slow through it. This is something that we need in the last chapter, and the place to read about it, one place to read about it, is down here in chapter 3, section 3.1 and 3.2. So it's these two sections here. So it's about 10 pages. And we're going to be working on this today and also next time. I don't want to just put it all out there. This is a difficult topic, and we're going to try to take you through some of the main examples that we're going to be using. So change of measure. This is the first topic, and then after the break, we'll switch gears and we'll do something a bit different, and we're going to start on American options. Okay, so before the break, we'll do this change of measure, and then after the break, we'll do American options. Okay, so let's just recall some of the things that we have been we've been using. Right, we've gotten familiar with Fn. This is a sequence, typically up to n, or later in section 5, we will actually have Fn going from 0 all the way up to infinity, not including infinity, up to infinity. Right, so this is a string of sigma algebras. So each Fn is a sigma algebra. So remember what that means. It says if you take a set, inside the sigma algebra, then you're guaranteed that the complement is in there, the empty set is in there, and then the thing that the letter sigma comes from this ability to take countable unions. So the union of Fn belongs to F when Fn belongs to Fn for all n. So I should say maybe Fm. So I should using the same letter for too many things. Call this for n here. So each Fn is a sigma algebra, and then you have this property that the increase is an increasing structure. So when you have that, you're going to get a filtration. So we call the Fn just round up to n. This is all we need today. We call Fn for a filtration. Okay, so we talked a bit about this, and of course, for us, the main example that we have is when we take Fn to be the sigma algebra generated by psi1 up to psi n. We take the initial one to be just a trivial one. Right, so what this here means is, what does this notation here mean? It means that if I look at the set psi k less than some number x, right, this is something that belongs to Fn for all k running up to n, and for all x, like that's what this symbol here means. This means that you have this property, and it's this here is what it means to be measurable. Right, this here means that psi k is Fn measurable. Like, and then the symbol here says that not only do you have this property, but Fn is the smallest sigma algebra with this property. So Fn is the smallest sigma algebra such that psi k is Fn measurable for all k running up to n. Okay, are there questions on what this is? Stuff that we have used before the midterm. Are there questions on it? Now will be a good time to ask. Okay, so I'm going to move one step further. Now comes the next material here. This is going to be new, right? So we call P a probability measure. On, say, let me use a different letter. Maybe call it G. This is a sigma algebra. If there are two properties that it has to hold, the first one is that if I take omega, let's take it into P, I'm going to get 1. And the second property is that if I take a union, so this is where that property up here comes in handy. this is where this property here comes in handy, that union of G M, this is equal to the summation of the individual probabilities when, well, so first of all, GM has to be measurable and you have to be disjoint. That's a probability measure. We have not used this for us. We've just specified. For us, we had just specified that. So we only said that the probability of psi n being d would be equal to p, and we said that the probability of psi n being u, this is equal to 1 minus p. We didn't specify p here as being, a function that has the properties here, right? So p here goes for, has domain G and takes values between 0 and 1. Like the domain of a probability measure is a sigma algebra. And so here, so that's all we said, right? So we could have said instead we should say here that P goes from we could say down here that P is a probability measure that lives on, for example, Fn, and taking values. This is a function. This is a measure. It's a probability measure. Such that these two up here holds. But we were not being very specific about what kind of sets that we were allowed to put into, that we were allowed to evaluate P on. But now, if one wants to be more precise, you need to specify the domain of the measure. And so here, this could be, for example, Fn. It could also be, so often our P is defined on, say, F capital N, which is that sigma algebra that is being generated by the first n tosses. So often this is the case. Our P is defined on this, and then we use that. If I look at, say, psi n being d, this is okay. This is well defined because if I look at the set when psi n is equal to u, this is an element inside Fn, and Fn is inside F capital N. This is true for any n running from 1 to up to capital N. Okay, so when we're talking about this change of measure, which is what we're going to be doing now, it becomes important where the measure P is defined. So this is what I'm trying to be more specific about now. Very often our P is given up to some capital N here, say 100. So if you have a 100 period model, then it's defined on F100. Right? But then it also means that you can look at those sets here. Right? So if if n is a 100, so this is a 100 period binomial model, so you're looking at a 100 period binomial model, then if I look at psi 50, the 50th coin flip, this is if 100 measurable. That's all I'm saying up here. And so it means that if I have a measure that is defined all the way out to the end, well, I can talk about the probability that the 50th coin flip takes values U and D. Any questions on this? Okay. There are some loose ends we have to tie up, like so. So one thing that was like missing in the analysis before the midterm was that we had P, that was a number between 0 and 1, and we had P tilde, right? And there was a formula for this P tilde. So it was given that psi n would take the values U and D with probability P here, and that these psi n's, they were IIDs, independent and identically distributed. This was given to us. However, we used that if I would look at them under the P tilde probabilities, then the probability of going up would be P tilde, and this would be 1 minus P tilde, and then D. And then we were using that these were also IIDs under P tilde. So one thing that is missing here is that we were given a certain structure under P. Now, how come we can use those properties not under P, but under P tilde? Like, there was a mismatch, what was given and what we used. Like, how come that we are allowed to use these properties that were given to us under P? How come we are allowed to use them under P tilde? There seems to be a mismatch. If we had been given the last properties here under P tilde, then of course we could use them, but we didn't do that. Like, we created this P tilde, these probabilities, by some martingale condition, right? That the expected, that if you took the stock and you discounted it, you would get a martingale. This is how we found the P tilde expression. But we also used, for example, that you had these coin flips, you were independent on the P tilde. Now, why is that true? Because you were only given that you were independent on the P. Right, so what we should need, so one thing we need to do is we should check. We should check, for example, that psi 1 is independent of psi 2 on the P tilde. And so you're given, so how would one do that? So on the P, right, if you were to check for independence, you could compute the joint moment varying function. On the P, you would have, if I looked at the joint moment varying function, so this would be EIA1 psi 1 plus I2 psi 2. Like, you could, given that you have independence, you know that the characteristic function has the product structure. If you don't like the I, you can throw away the I and you can do the moment varying function. This is okay. And you could also do this one here. This is the joint characteristic function. Here, A1 and A2. The numbers in R. This is the joint characteristic function. You could also use. You could also use. So this is just an alternative. Just an alternative. Let me write it in a different color. You could also just use the moment engineering function. So A1 psi1 plus A2 psi2. A1 psi1 times A2 psi2. A1, A2 are in R. This one here would be the joint moment generating function. And so this is what is given to us. We are given that this holds on the P. But if we want to have independence on the P tilde, we need to check. We need to check that the expectation, for example, if you want to do the characteristic function, you should check that when I compute the expectation under the tilde measure, I have the same property. Right, so everywhere instead of E's, I'll put E tilde. Right. So we're given that it works for P, but we're using the property on the P tilde, so I need to have this property. Or alternatively, if you want, you can alternatively, you can forget about the I and just do the joint moment. Let me write it out again. That you have this property not under P, but you have it under P tilde. Right, so we're given this. We're given these two properties, either one, they are equivalent in the case that we'll be looking at here with coin flips. And now how does one check that you have the same property but under the P tilde measure? So this is what independence means, right? You have independence. This here is independence. Right, independence, this is equivalent to these functions having the right multiplicative structure. Are there questions on this? You guys are very quiet this morning. This is a good time to ask some questions about independence.
Professor, I have a question regarding the alternative. I see that the difference is that there's no I, and could you explain that?
Yeah, right. So if you looked up our textbook, I think it's in this one here. He has so this is the second one. So if you look up here under independence, so this is 2.253. If you go in here, you'll find like a number of equivalent. You can see here these examples here. This is about coin flips, right? This is what we're talking about, even though this is in the second textbook. Right? So there's lots of material in here. You can see he writes here like heads and tails and so on. And if you go over and see this theorem here, this is what I'm referring to, right? So you have independence, and then a number of equivalent conditions, right? So you're saying that independence, this is equivalent to saying that the distribution factors. The one that I'm getting on is this one up here, because all these properties are fine. Yeah, if you have densities, then the density has to factor. If this happens, if and only if you're independent. In our case of coin flips, we do not have densities. In your next homework, I put a question on there, something about uniforms, and there you will have densities, and then you can write this. Right, so the one I'm getting out on here is this one here. This one here, right? And so the problem is that he has this feature over here where he says the expectations needs to be finite. And I'm not so this is fine. You can do that, but one way to circumvent this statement is to put this I in there, right? Because if I put the I in there, this here can explode. This one here can never explode. And let me just try to elaborate on this. So what is the benefit? What is the benefit of using characteristic functions over moment uniting functions? Well, maybe an example could be could highlight it. So if I would do an example where I would say, let me take X to be standard normal. Right, so this has a mean and variance 1. And then I could look at the expectation of e to the ax, the standard normal moment uniting function. I can write this here out as 1 over root 2 pi. I use the density, I integrate over r, I get e to the ax, and then the density was e to the minus 1/2 x squared dx. This would be the moment generating function, right? This here would be the moment generating function. That is this guy. And then I can also look at the characteristic function. Now I have to put an I there. I do an AX. The formula is very similar. E to the I AX, and then e to the minus 1/2 x squared dx. At some point, there was a lecture where we did this, and the name of the game is to realize that you can, there's something about a square here. You can factor out a square here, and the same thing, you can factor out something with a square here. These things can actually be worked out. We did it at some point. Let me show you how one might be able to do it quicker if one just jumps into Mathematica. Just get down to the bottom. So if one were to integrate, the thing that we're talking about was exponential of a times x times the density. This was exponential of minus x squared divided by 2. Everything divided by square root of 2 pi. This was the moment generating function, and we want to integrate x from minus infinity to infinity. So we ask Mathematica to do it, and you get this exponential. Let me just write it here on the paper. This is an exponential of a squared divided by 2. And of course, I can do the same thing. I can ask Mathematica to calculate the characteristic function. The only difference is I have to put an I in here. I think this is that capital I there. Now I'll do that. I get basically the same formula. There's just a minus instead. Okay. So this gave me the two formulas here quickly, or I could have done it by hand. We did that at some point before the midterm. So this all looks good, right? We have the moment generating function, right? And then we have the characteristic function. The characteristic function is this one. A here is just a number. A here is a number in R. A here is a number in R. And Eddie's question is like, why would I move into this one instead of that one? Well, this example here can be tweaked just a little teeny tiny bit. What about if I, instead of X, just try to calculate E to the A, but now my random variable instead of X is going to be X squared. Well, I use the formula. How do I alter the formula? Well, it's still a function of X. So I take that function. This is E to the A, and then it's an X squared. And the same thing with the density. But now you can see there's trouble, right? Because if A here is big, this thing explodes. If A here is big, this explodes. But this here is equal to, for example, if I take A to be, let's take A to be a half. If I take A to be a half, then what do I get? I get a half here, minus a half here. D will cancel out. I'll integrate 1 from minus infinity to plus infinity. This is equal to plus infinity. So it explodes. And this is what Steve is getting at when he writes over here. You need this word finite. Now let's have a look at what happens over here on the other hand. E to the AI x squared. Well, if I took absolute value of it, this is a complex number, right? We're taking the expectation of a complex random variable. So this is a complex number. If I moved the absolute value inside, so I'll have e to the absolute value of e to the IA x squared. Well, now what I have inside here, does anybody know a good bound of this one?
Is it 1 and -1? Something?
Yeah, so when I take absolute value, this is equal to 1. Right, so this here is equal to 1, no matter A. Right, so this one here does not blow up. And this one here potentially blows up. And you can see this A is equal to a half. This is a critical point. So of course we can go back to Mathematica and ask Mathematica to fill out all these details. So let me show you just how to do that. It's just a little change to what we already had. All right, so now we're looking at Mathematica. And so if I were to look at the moment generating function, but for the random variable x squared, I'll have to put a square there. The rest is the same because this is the density of x. And now this is the thing that can explode, at least when A is equal to a half. And if we integrate and see what Mathematica tells us, there should be some trouble in paradise here. And you can see it is, right? It gives me this formula here. And there is a requirement that says that the real part of A, in our case, A is real, right? So it says that A should be less than a half if you want to get something that's finite. Consistent with what we had on the paper, right? What we had on the paper was that if I took A to be a half, it would explode. And now the difference is that if instead I would work on the characteristic function and I'll put a square. Now we should be good. This is going to be a complex number of length less than or equal to 1. And let's see what we get. If Mathematica can calculate it. And there we go. That's the formula. That's the formula for the characteristic function for the squared normal. And you can see here the condition is on the imaginary part, but A is real. So the imaginary part is 0. Right, so this condition here is trivially satisfied because the imaginary part is 0. 0 is bigger than -1/2. And there you go. The characteristic function is does not explode, which is of course consistent with what we had here. It has to be bounded by 1. So this is the reason that I prefer the characteristic function is because I'm guaranteed that it never explodes. If I were to work with a moment-determining function, I always have to worry about when does the thing explode, if it explodes. And by putting in that I here, I never have to worry about that. For the particular application we have in mind, when we just have coin flips, this is an irrelevant detail. You can work with either one. It's going to be perfectly fine. But you can see if you were to work with a normal, you run into this problem, right? So normal squared, this is what people call a chi-squared distribution. Chi-squared distributions, you have this this issue that the moment-determining function explodes. Does that make sense?
Yes, thank
you. Yeah. Are there other questions? So I want to highlight once again that when you're talking about independence, like this here is an equivalent condition to being independent. And there are many others. So let me just bring up that theorem again from the second volume. Right? There are lots of others. This is condition 4. If you have a density, then this is condition 5. But the thing that is not equivalent, right? This is what he writes here. The conditions above, they are stronger, and they are not equivalent to this one here. This one here is 0 covariance. Right? This is not equivalent to being independent. It is implied by independence, but there's no way you can go from here to what you have up here. It's not true. Okay, so just keep that in mind. 0 being uncorrelated, this is not the same as being independent. Any other questions before we continue? Okay, so let's go over it again. We're given that we have independence of these coin flips under P, but we're using the property. Whenever we price something, we will compute expectations under P tilde, right? So we would have these expectations under the tilde measure everywhere. And we're using this property that we were given under P, but we're using it under P tilde, right? So it seems like there's a problem because just because I'm independent under one measure, why would I necessarily be independent under other measures such as P tilde? And so there's a gap here in our analysis, and I'm trying to fill out that gap. Right, so how do I check these properties? How do I check this one? How do I check that one? Well, what I need is to somehow bring these expectations under the tilde measure back to something that has to do with expectations under P. Right, so the connection between P and P tilde, the connection between these two can be is given by and so here comes the new word, the radon a Nicodim a derivative. So it's an unfortunate thing that it's called a random derivative, right? So this is, we have seen the word derivative now in many, we have seen many uses of the word derivative, right? So this here is not like f prime of x. This is not like that. And it is not, this is not like an option. This is not like a put or call. Because f prime, this is also something that we also call a derivative. We talked about put and call options, and we call those derivatives as well. So here's a third use of the word derivative. And this random-Nicodim derivative, this is on its own category. It's just called the random-Nicodim derivative. And so if you switch over to the first book, this is where you'll see the title of that section. Like this is where you find the word random-Nicodim derivative. So I want to talk to you guys about what a random-Nicodim derivative is. So a random-Nicodim derivative, this is this connection between P and P tilde. It's denoted by, the notation is, it's denoted by this dP tilde dP. It's denoted by that. This is the notation. It's a random variable, so it goes from omega, and then it takes values over that are positive. So it's a positive. What this notation here means is that this is a positive random variable. And it has one more feature. It's a positive random variable. And the second one is that if I take so it's a random variable, so I can take expectation of it. So if I take expectation of the thing, I will get, I'll get 1. So it has the expectation. This R, this is going to be denoted by Rn. The expectation of any random-Nicodim derivative is 1. So the notation is this dP tilde dP. Sometimes maybe I shouldn't say sometimes, often in the text that we are using, often you also see Z and the Zn being used. So those are also letters that the textbook will use to denote this dP tilde dP. So what on earth is this thing? Well, maybe the easiest way to get our hands on it is to look at how this works in an example. So here's a typical example. This is actually Black-Scholes. So this is to really be fleshed out in 621 and 623. But here's a typical example of how this thing is being used. So you take a random variable like the one we just had. So take X. This is standard normal. Right. So that means that the probability on the P of X being less than a number X is given as an integral from -infinity to X. And then you have the density, and the density is this 1 over √2 pi e to the minus 1/2 y squared dy. That this is true for any x in the real, on the real line. Right. And so you see this is a p, so the probability, the density under that measure has this form here. That's the density, right? And this is the distribution. So the distribution is given by the integral of the density. And if you have a standard normal, that density has this particular form that we just used before. So there's no p tilde here. So let's try to create a p tilde. So let's try to create a new measure. Create a new measure. I don't want to call it p tilde because this is often just identified with the this binomial model that we're using. So let's create a new measure. Let me call it for q. So let's create a new measure q, and this is going to be on that sigma algebra that x generates. So this is the smallest sigma algebra. So again, this is the smallest sigma algebra, which makes x measurable. So how does one go about creating a new measure? Well, now this is where we're going to use the Radon-Nikodym derivative. So what we're going to do is we're going to say, so what does it mean to create a new measure? Well, we need to create something. We need to create something that satisfies. Right, we need to create something that satisfies these two properties here, right? So it has to be that P of omega, in this case, is going to be Q. So Q of omega has to be 1. Q of a disjoint set, you should just be able to sum them up. So we want to create a new measure, and how are we going to do it? So we're going to say Q on a set A. Then we're going to define what this thing here is. We're going to define this as an expectation. We're going to define this here as an expectation. So an expectation. So this is an expectation with respect to P of what? Well, I want to have the indicator for A. Right? If I just did that, if I close the bracket here, then this would just give me P of A. So this means that Q and P are the same. So that I don't want that. I'm going to put something else in here. And the thing I'm going to put in here depends upon X, right? So I normally distributed random variable. I want to put in an expectation here. I want to put in a dq dp. Okay, what should I call my dq dp? What should it be? It has to be a positive random variable. That's one of the requirements, and it has to expectation 1. So what I want to do is I want to put in e to the x. And that's a positive random variable. It's strictly positive, but it doesn't have expectation 1. We know what the expectation was from the calculation we just did, Mathematica did. The expectation of this quantity here is e to the 1/2. So I need to correct with that. So I need to divide here. If I want the expectation to be proper, to be equal to 1, I need to divide by that expectation here. Right, so this here is my Radon-Nikodym derivative. This is my dq dp. Of course, we can, right, so it's this thing here, this box here. This is my Radon-Nikodym derivative. And of course, I can plug in here what the expectation was. We can write this was e to the, what was it, e to the 1/2 and if you want to, this is a constant, so we can even put them outside here. So this is how I'm going to define my Q. this is true for any set A. I want this Q measure to be defined on the sigma algebra. So this is true for any set A that's inside here. So this is an example of a Radon-Nikodym derivative. This Radon-Nikodym derivative here, it is positive and it has expectation equal to 1. What remains to be checked is we need to check here, check that Q indeed is a probability measure. I said over the two properties from slide back, slide what was it, slide 2, slide 3, slide 2. There were the two properties we have to check that this new creation here indeed is a probability measure, and there are the two properties. It has to be that when I evaluate the object at omega, I get 1. And when I take a disjoint union, I just sum up the individual probabilities. So I need to check these two properties. So property number 1 is if I take Q and I evaluate it at omega, keep in mind omega is in all sigma algebras, so this makes sense. I can take A here to be omega. And what would I get is, I'll get that this is equal to E to the minus 1/2. And then instead of A here, I'll put the expectation of 1 omega, and then E to the X. But 1 omega, this is everything. So this is equal to E to the minus 1/2 expectation of E to the X. But that expectation just calculated, that was exactly equal to what I had over here, 1 over it. So these two things, they reduce, and it just gets to be 1. So that was the first property. We need that the expectation is equal to 1. And the second property is this disjoint union. So let me show you this for the case. We start out, let's just do a simple case. We also need to check. The second property is that we need to check that if I take sets, let me take sets that are disjoint. So let them be in M, and let's take GM intersection here with GN. This is empty. Whenever N is not M, then we need to check that Q evaluated at that disjoint union. This is just a sum. So let's do the case. Let's do a simpler case. So let's try. Let's do Q over, say, G1 union G2. It's not quite what we need, but maybe this is good enough just to get an idea about why this creation here works. Let's do this one. Why does this one here work? Well, I'll use the formula. We always have to use the formula. So the formula for a set A, given according to this mess here. So I'll have E to the minus 1/2 expectation. And then I have, instead of A, I have G1 union G2. I have 1. And then the indicator for G1 union G2 times this expectation times this exponential of X. Now, how can I write the indicator for G1 union G2? How can I write this? Well, keep in mind G1 and G2, they are disjoint, right? So over here, this is my sample space, omega, right? So I'll have in one corner, I'll have G1, and say in the middle here, I'll have G2. Right, so the indicator for the union is equal to what?
Would it be like the sum, so 1G1EX plus 1G2EX.
Very good. So you get that. And now you can see you're in business because the expectation is linear. So this here becomes e to the minus 1/2, and then 1G1 times e to the x plus, and then the same thing is e to the minus 1/2, e, and then 1G2 e to the x. But now we use the same, we use the definition of Q. This is Q of G1 plus Q of G2. And that's what we wanted to prove. So this here only shows it. This only shows it for the case when you have G1 and G2. So you need the general case. So for the general case, so this is Q of a countable union. We need what's called the monotone convergence theorem. And it is in here. And you can find it. It's in here in the second textbook on continuous time. So if you flip over to the appendix, not the appendix, into the table of contents, you will find it over here somewhere. So the monotone convergence theorem, this is page 26. So it's stated up here. I'm not going to take you through this. We will need this at some point, and I was hoping to this last piece over here on how to extend it from just a finite union to a countable union. It relies on this monotone convergence theorem that we have here, and we're going to be talking about this monotone convergence theorem in a few weeks, and I'm gonna hold off doing this. This here is going to come later. This is coming later. We need this monotone convergence theorem. This is something we need for chapter 5. So the first part here, this just serves as a motivation to give the remaining pieces, the remaining part, like where you extend this to a countable union. There's going to be something about moving limits in and outside expectations, and one way to do that is using this monotone convergence theorem. So that's all I wanted to say about that part right now. This here is the this way of creating a new measure Q using normals and exponentiating them. This is what Black-Scholes does. In the Black-Scholes model, this is how these neutral measures are created here. And so this is something I'll come back full blown in the courses in the spring. Any questions on what we're seeing here? So this was one example. So what other examples are there? I have a list of other examples that I think we should go through. So so formally, so a definition. So I should write down what the specific definition is. We say that so when Q has the form is an expectation of 1A times a random variable Z for any Z, for any A, say in G. So when there exists a Z that goes from omega over into the positives, and the expectation of Z is 1, and this formula here is true, we say, we write dq dp is Z, and we call Z Q's Radon-Nikodym derivative. And this is on G. So that's what it means to be a Radon-Nikodym derivative. It's something that is non-negative, and it's something that has expectation 1, and this formula here holds. So often we have this G up here. Often we have like Q of A is given by some Radon-Nikodym derivative, let's call it Cn, for A in Fn. Then you use that, well, if n is increasing, so this thing here is bigger than if little n. So in particular, this formula here, it works for not just A in the big one, but it also works for any A in smaller ones. So Q of A is equal to the expectation of 1A times Cn for A in Fn. N is smaller. And then we can use that the conditional expectation, we can use that the conditional expectation has this property that if I take the expectation of the conditional expectation, if I take here the conditional expectation on Fn, I get the correct unconditional expectation. It has this unbiasedness property. And then I can use that 1A, A is in Fn, right? So this one here is measurable. You can pop outside. And I can write this here as 1A. And then the conditional expectation of Cn given Fn. So you see you're stuck here with this conditional expectation here. This here is often denoted by Z little n. So you start out with a C capital N, and then you get the C little n by doing the conditioning. And so the miraculous thing is that, so this is a little lemma. This is a little lemma. It says, let Zn capital N the C capital N be a Radon-Nikodym derivative, so let it be a random variable that goes from omega, and say that it's positive. Say that it has expectation 1. Then this process here, the C little n, the one that came up, this is this object here for n equals 0, 1, of the capital N, this is miraculously a martingale. So I take a random variable, it's integrable. In this particular case, it's positive. Positivity does not necessarily matter for the conclusion, but it does matter for all random income derivatives. They are positive random variables. That's why we took the x in the example before, the exponential function in the example before. And so I'm keeping that here. The property that I want to prove is that the conditional expectation has this martingale property in it. Right? So I have capital N here, I have little n here. This is a martingale. And I'm going to just give it a shot and see how the proof would go. The proof would go by saying I take the process at a later time. So I take Zn plus 1, and then I condition on Fn. So remember, when you check for martingality, you have to condition. It is not enough just to take the expectation. You have to condition. And then you have to prove, that this conditional expectation is just equal to Zn. Let me try to work it out, right? So the first line of business is to plug in what is Zn plus 1. The first line of business is to plug in what is Zn plus 1. I use the formula. So Zn plus 1, this is C capital N given Fn plus 1. Right, that was my Cn plus 1. I didn't have the condition on Fn. So now I have two sigma algebras sitting next to each other. So the first one here, this was the definition of Cn plus 1. The next one here is going to use the property that Fn is inside Fn plus 1. So when I have two conditional expectations sitting next to each other, the smallest one wins. The smallest one here is Fn. So here I'll have E, then it'll be Cn given Fn. Right, so first I plugged in the definition of Cn plus 1, stuck it in here. Now I get two conditional expectations next to each other. If there is an ordering between them, one is bigger or smaller than the other one, the smallest one wins. And here Fn is going to win. This is the one you end up with in the end. And then the last one, now I'm just going to use, for this one, it's going to be the definition of Zn. Right, the definition of Cn will give me that I have that property, right? So that's the proof. I have a martingale here. So very often you're giving a random derivative, and this martingale that you get out of it, this process Zn, which is equal to the conditional expectation of C capital N given Fn. This is called the Radon-Nikodym derivative process. Right, so it's a long word, but this is why the title of section 3.2 is called the Radon-Nikodym derivative process. It is the conditional expectation of the Radon-Nikodym derivative. So this is the conditional expectation of the Radon-Nikodym derivative. And it's a martingale. So that's its key feature. It's a martingale. This one here has expectation equal to 1. So if we take the expectation of Zn, so let's write some other features. other features of this random derivative process. Well, one, it goes from omega over into the positives. It's a conditional expectation, so it's going to be measurable with respect to Fn. Cn is Fn measurable. And the third one is if I compute the expectation of Zn, like I have to compute the expectation of this conditional expectation. So I'll take the expectation of the conditional expectation. Right, so again, I have an expectation, have a conditional expectation, which one wins? It's going to be the expectation that wins. This is the expectation of Cn. Right, but that was given to be 1. So it has a lot of good properties, right? So the first and perhaps most important one is it has the martingale property. Then it's a positive random variable. It's Fn measurable and has expectation 1. So there are lots of good properties of this random derivative process. I was thinking about we should look at some examples, but before I dive into some more examples, are there any questions on what we have up to this point? So these random derivatives, they can be pretty tricky to wrap your head around. This is a difficult topic, and so I want to do some examples. The first example is quite similar to the one we had with the exponential. Let me try to find that exponential example again. So this was the one we had here, where we had the exponential. So let me try to generalize this. Right, this is just one random variable. Like, so we have a process, you have a collection of random variables. If you just have the random derivative, it is a single random variable. When if you then form the conditional expectation, you want to have a collection of them. So let me try to create a random derivative process. So let's say that delta Bn, these are standard normal IIDs. The standard normal IIDs. And then my Zn, my random derivative, is going to be defined as an exponential. As an exponential of what? So I need my process B0 is going to be 0. So I'm going to define this process here inductively. So Bn, this is going to be defined as Bn minus 1 plus this delta Bn. But this is how I get my B. The Bn's, the delta Bn's, they're given to be IID, and then I define these Bn's as follows. Right? So this is recursive definition, starts out at 0, and then I'm just going to add up these increments to get the value at time. So what is my random derivative process? Here, well, it's going to be Bn minus 1/2 times n. So I'm claiming that it has all these features that we have listed up here. And so you can see it's positive, right? Because it's an exponential. You can see that it's Fn measurable. Yeah, this is true, right? I'll have my Fn. This would just be the sigma algebra generated by B0, B1 up to Bn. So that's going to be true. What about the martingale property? Let's check that this is a martingale. Indeed is a martingale. And how would I do it? Well, again, you take the process at time, say Cn plus at time n plus 1. You compute the conditional expectation given the first n observations. So this is Fn. And then you plug in what Cn is. The Cn plus 1, I use the definition. This is e to the Bn plus 1 minus 1/2 times n plus 1, condition on Fn. And now we're in a situation that lots of you were in when you did the midterm, right? How do I calculate a conditional expectation? And so what we need to do, well, the strategy that seems to work really well is to express the random variable that you have inside here in terms of something that is measurable with respect to Fn and something that is independent of whatever generates Fn. So something that is independent of Bn minus 1 all the way down to B1. Okay, so we need to break this thing here and we need to decompose it into two parts, something that is measurable and something that is independent. And let's write it out. The decomposition here, let's just plug in what Bn plus 1 is. Right, so we use the formula for Bn plus 1. This is equal to Bn plus the change Bn plus 1. The second part here, this can be moved outside. Exponential of a sum is equal to the product of the exponentials, and this one here has no randomness in it. It can be moved outside. So I'm start with the expression e to the Bn plus delta Bn plus 1. And then I move the other term outside. And so now what I have here is this very familiar situation that you guys also, many of you also had in the midterm, right? This is measurable, and this one here is independent. Right, so you take out the thing that's measurable, e to the Bn, and then what is left inside is e to the delta Bn plus 1, but this was given to be IID, this was given to be independent. So now here we use that delta Bn plus 1 is independent of B0, B1 up to Bn. And then we just have the, like there are two properties, is this one, and we also using the Bn is Fn measurable. Using these two properties to get that equality sign. So here we have delta Bn plus 1 e to the minus 1/2 n plus 1. And then we're almost there, right? What is left now is to compute this expectation. But this is the moment generating function. This is the one that we've been working with. This is standard normal. Right. So here, this is the moment generating function. This is the moment generating function. So I'll have e to the Bn, and I can borrow this minus 1/2 from over here. Minus 1/2 n. And then the moment generating function, this will be e to the 1/2, because this was standard normal. And then I have e to the minus 1/2. And we can see that these two cancel out. And I'm left with the first term. This was my C. So this object up here, this is a martingale. In particular, for n less than capital N, when I compute the conditional expectation of this is Zn given Fn, this will just give me Cn. And that is a martingale. We proved that this object on the left-hand side is a martingale. In general, we proved directly here that Cn is indeed a martingale. Any questions on this more elaborate version of of the example we had, where we just had an exponential of a fixed random variable. Now we have a stochastic process. This is what gives us this random equivalent derivative process. Are there any questions on this part?
I had a question when you applied the moment generating function to the expected value of e to the delta bn plus 1.
Yeah.
As well as wasn't sure also how the factor on the right of that also becomes just n plus 1 becomes 1, I guess.
Well, so see, I had my EBN here. That was the first part. Right, and then I borrowed from over here. I just moved that part over here. So I took the minus 1/2 n, put it here. If you don't like that, we just keep it over on the other side. Maybe this is clear, right? So this term is the same as that one. This term here is the same as that one. And this term here is the same as that one. So the moment generating function, the moment generating function was what? Let's flip back to the where we had the thing that was the one that we got copy pasted from Mathematica. That was this one here. If I had a standard normal, and if I were interested in the moment generating function, I would have this formula here for any a in R. So in particular, if I take a to be 1, if I take a to be 1, then the expectation of e to the x is just equal to e to the 1/2. Right? Because a squared when a is equal to 1 is just 1. So I get e to the 1/2. That's going to give me the expectation of e to the x. Right? So then you see there's no constant code. The constant out here is a 1. And delta bn plus 1, this was standard normal. So this expectation here will just become this e to the 1/2 here. You're not buying it. If you go back, another way to try to see this would be if you go back to Mathematica. So if you're looking up here, if I'm integrating, this is the moment generating function for a standard normal, right? So if I take a to be 1 here, and I run it, I'm just going to get this square root of e, or e to the 1/2. Does it make sense?
Yes.
Great. So that's how we got the that's how we got the middle part, right? And then the other parts, this is just a question of reordering, right? So I had plus I have here, minus I have here, they will cancel out. Then I have e to the bn minus 1/2 n. So I'll combine these two and I'll get exactly the same. Are there other questions, comments? I have 2 more prepared, so let's try to do another one. This one here is also going to be in one of the homeworks. So another one. The this one here, this is going to be our binomial example, and you can find it in section 3.2. This is the binomial example. So what Zn is here? Zn here is so it's defined as p tilde over p, and then it's to the power and the number of heads in first n tosses. So P tilde, this is, we're in this binomial example where we have IIDs, such as the psi ends, the IID, right? We have this probability of a U and a D. This is P and 1 minus P. And your P tilde, this is there's a formula for P tilde that I always forget. That's the one that goes on top, and then it's the ratio P tilde with P, number of heads in first n tosses, and then you do times 1 minus P tilde divided by 1 minus P. This is going to be the number of tails in first n tosses. And you might recognize this as something that is not very far away from one of the sample problems that you guys worked on for the midterm. Like, so we're claiming again that this here is a martingale. Again, you'll see that Z0, well, is equal to 1, because there's not going to be any tosses. It's positive. And what about the martingale property? Do we have a martingale here? So now we look at the filtration. The filtration in the binomial model is always given by these coin flips. Those ones we have here. So can we prove that this is a martingale? Well, the recipe is more or less the same as before. More or less the same as before. What we would do is, we would have we would take the expectation of Zn plus 1, condition on the first n tosses. So we call this Fn. And we have to prove that this is equal to Cn. So the first line of business, maybe I should just simplify a little bit, and it's just a bit long to write this every time. Right? So I could call this quantity here. I could follow the textbook. The textbook calls this for Hn. I could call this here for tail. So that'll be naturally, it'll be natural to call this for Tn. What I'll have here is I'll have an expectation of Zn plus 1. So this is P tilde divided by P, everything to the power Hn plus 1. And you do the same thing for the other quantity. This will be, and of course, when I add them all, I'm just going to get n, right? Hn plus Tn. This will just be the number of heads plus the number of tails. This will just give me n. I mean, it's very similar to saying that sometimes we call the top part here for Q tilde, but of course, Q tilde plus P tilde has to add up to 1. So Q tilde is 1 minus P tilde. There are many ways to write the same thing. This is all fine. So we'll have this expression. And it's so the situation is very, very similar to what we just did, right? We have a random variable, we're conditioning. And so how do we proceed? Well, the recipe is always the same, right? We have a random variable, we condition. We have to decompose this randomness in here into two parts, right? You have to decompose it into something that is independent and something that is measurable. So let me try to do it. This would be the expectation, and then the number of heads in the first n plus 1 tosses. I can write this as the number of heads in the first n tosses. That's nice because this is going to give me the measurability part that I'm wanting. But then, of course, there's also the n plus 1th toss. So this will be P tilde over P. And I'm wondering about this thing here being heads, right? So I could lift this up to an indicator for what is the n plus 1th coin toss. This is psi n plus 1. And what do I want it to be? Well, I want it to be heads. So I want this psi n plus 1 to be u. So that would be one way to express hn plus 1 is hn, and then this mess here of an indicator. And I can do the same thing for the tails. I'll have 1 minus p tilde over 1 minus p. This will be to the power tn. And then 1 minus p tilde over 1 minus p. This would be the indicator that the n, that psi n plus 1, I need a tail, so this has to be equal to d. Right, and then the condition on fn. And you see what this decomposition did? It broke it down into something that is measurable, right? I can combine this term and that term. They only involve psi 1 up to psi n. I'm conditioning on those, so I can take them out, the immeasurable. And then what remains is this product of these two, that is psi n plus 1, but that's independent. So the situation is very similar to the one we just had. I'll take out what is measurable. I'll take out what's measurable. So this is p tilde over p to the power hn. I'll take off the other one too. This is 1 minus p tilde, 1 minus p to the power tn. Right, and what is left inside now is going to be independent of fn. This here will be the unconditional expectation of p tilde over p. The indicator that psi n plus 1 is u times 1 minus p tilde divided by 1 minus p to the power indicator psi n plus 1 is d, and then no condition. So now what is outside is exactly my zn. So that is cn. And then I have to compute this expectation. Then I have to compute this expectation. All right, so when I compute the expectation, there are two possibilities, right? Either psi n plus 1 is equal to u, or psi n plus 1 is equal to d. Okay, so I'll have this outside. So I'll take the probability p of it being u. So this is p times, and then it is p tilde over p. That was the first one, right? And then the second one, this here is equal to 0, something to the power 0. This is 1. So that will be the first one. Plus, and then I am on the set where psi n plus 1 is equal to d. So this will be happening with probability 1 minus p. And then I evaluate this thing in here when psi n plus 1 is equal to d. The first part, this is going to be a 0. So that's something to the power 0. This is a 1. And then the other one, this is now a 1. So I get 1 minus p tilde divided by 1 minus p. And so you see the situation is quite similar to that one, or at least that one problem in the sample sheets, or I think it was also in a homework. They will cancel out. I'll be left here with exactly cn. One p and the p's cancel, I get p tilde. 1 minus p cancel, I get 1 minus p tilde, I'm left with a 1. So this is also a martingale. That was the binomial example. So the previous example was the Black-Scholes example. Now we have the binomial example. Are there any questions or comments on this part? So this is another example of a positive martingale. So the expectation of this thing is always equal to 1, simply because it starts out at C0 is equal to 1. The last example I had in mind that we should do is, this is an example. This here is lemma 5, 2, 1. So it's a bit something that's coming a bit later, but it's quite similar. It's quite similar to the one that we had just done. There's more structure on the size. So we're going to do psi n. This is going to be you're going to be IID, but you're going to be symmetric. You're going to be symmetric. So the probability of going up is a half, and the probability of going down necessarily must then also be a half, and it goes up with 1 and it goes down with -1. So this is a this is symmetric. Let's call it symmetric random walk on the integers on Z. Right, because it always goes up by 1 or go down by 1. So if you start the process out at 0, it'll go from 1, then it'll go either up to 1 or down to -1, then it'll continue. It'll always take values that are integers. The process in question this time, is e to the, so we just minus the n this time. Cn is e to the sigma. Sigma is a constant, and then mn. So I also need to tell you what mn is. This is just you add up the size from 1 to n psi I, and you started out at 0. So that's the symmetric random walk. You just add up these pluses and minuses. So that's an exponential. So now we get positivity. You have to correct it a little bit, and the way that you correct it is 2 divided by e to the sigma plus e to the minus sigma, and then everything to the power n. And sigma here is a constant. Right, so what is the claim? So we have a process here. It is positive. It's an exponential times something positive. This is a positive process. When n is equal to 0, this is equal to 1. M0 here, this is equal to 0. So Z0 again, it always starts out at 1. Same thing is true for this guy, right? C0 here is also equal to 1. And the next thing to prove is that, well, it's a martingale. It's a martingale. Okay, so we also need to make sure we understand the filtration. So Fn is going to be the sigma algebra generated by these still coin flips. So this is psi 1 up to psi n. F0 is trivial as always. What we have to prove is that this object here is a martingale. Let's try to go through the steps. They are very similar to the ones that we've done before. Let's go through them the last time today, and then we will take a break and move on to something else. Let's do the martingale property of this particular process. So let's see, what do we get? We have, so we need to take Cn plus 1, we condition on Fn, and then we compute the conditional expectation. And the way we proceed is, as before, we plug in the definition. It's going to be e to the exponential sigma mn 2 divided by e sigma plus e minus sigma to the n plus 1. N plus 1 here, n plus 1 is over here, conditional on Fn. So now we're in business. It looks familiar. We have Fn here, we have Mn plus 1 here. We need to decompose the randomness so we get something that is measurable and something that is independent. This part here, this is not random. So we could move him outside so we don't have to worry about him for now. E sigma, and so what we do is we use what Mn plus 1 is. Okay, so that is going to be Mn, and then we will have the last coin flip. This will be psi n plus 1 condition on Fn. Move this quantity here outside. There's nothing random about it. It goes outside the conditional expectation. And now we're in business because we have exactly that structure. We have Mn is measurable, psi n plus 1 is independent. The measurable part goes outside. And then this part is independent. So we just take the unconditional expectation. And we don't have to remember that factor over here. 2 divided by E sigma plus E to the minus sigma. Plus 1. We took the measurable part outside. This one is independent. In here we have the first n coin flips. The coin flips are independent of each other. So this one here is independent of it. Here we have an unconditional expectation. There are two possibilities. You have E to the sigma Mn. Each possibility is equally likely. You have a half and a half. So this is 1/2. And what else will we have? We will have E to the sigma. That will be a 1 plus E to the minus sigma. That's when this is -1. Take everything here times 2 divided by E to the sigma plus E to the minus sigma n plus 1. And now we can see these two terms, the mesh, I'll get one term fewer. This here will become E to the sigma Mn times 2 divided by E sigma plus E to the minus sigma, everything to the power n. Here we have n plus 1, but there's exactly one of these terms being multiplied on, and you will cancel out the 1. I'm just left with n. And then, of course, you combine these two and you recognize that this is your Cn. And that one here is the martingale property. So another example of a positive martingale with constant expectation equal to 1. So all these processes here, these serve as Radon-Nikodym derivative processes. We have seen now, I lost track, 3 at least. Those are the main examples that there will be, when we get into fixed income towards the end of the course, there will be another example of a Radon-Nikodym derivative process, but I think this is good enough for now. Are there any questions before we take a break? So the notation, the terminology, I should say, the terminology is a bit new, but as you can see from the calculations that we've been doing, what goes into working with these terms, it is what we're used to. It is the same story. We take out what's measurable and then use independence on the rest. So here we don't have to use the independence on it per se. Of course we could if we wanted to, but we don't have to because you're looking at an exponential function. An exponential of sums work really well. You can write this as a product, and then you can take out that term that is measurable, and then the other term is just going to be independent, and you just take the unconditional expectation. So this is all stuff that we've seen and worked with in the past. The terminology is new. This way of thinking about meshes, we're thinking about meshes now as being functions that have domains given by sigma algebras and codomains being 0 to 1. And in particular, this way of creating a whole slew of new meshes, like this way of creating meshes using random variables, and we use this formula. Like this is how you give me a random variable that has this these properties. It's positive, it has expectation 1. Then I can create a new measure simply by taking an expectation of that random variable over that set with respect to the old measure, the measure P. And in here, there's an embedded martingale. And so instead of modeling Z, we will often model a stochastic process, which we denote by Zn. And that process is then going to be, a martingale. and you will get the probabilities under that measure simply by integrating up the martingale over those specific sets that you're interested in computing the probability of. Are there any questions before we take a break? No, let's take a little break, and then when you come back after the break, we're gonna start talking a little bit about American options. So we're gonna leave this change of measure behind and do something else. Okay, so let's take a 10-15 minute break.